Welcome to The Explainer. Today, we're jumping into a topic that's, and I mean this, absolutely fundamental for any engineer: corrosion. And this is especially for all you students at the CSMS College of Engineering and Technology who are gearing up for exams. Don't worry, we're going to make sure you have everything you need.
So before we get into all the chemistry, let's just get real for a second about what's at stake here. Corrosion isn't just a little bit of rust on a fence. In your world, the world of engineering, it's a huge cause of structural failures, massive economic loss, and some really serious safety issues. So understanding this stuff isn't just for a test, it's absolutely critical.
All right, let's get the official definition down. Now, the two words you've got to lock in your brain are reaction and environment. This is so important. Corrosion isn't some property of a metal deciding to just fall apart on its own. No way. It's always an interaction, a conversation between that material and whatever it's surrounded by. Air, water, you name it.
So here's our game plan. We're going to talk about the real-world impact, then we'll dive into the two main types, that's dry and wet corrosion. After that, we'll look at some really common examples, and we'll wrap it all up with a summary that's tailor-made to get you ready for that exam.
Okay, so why is this a topic every single engineer has to basically be an expert in? Let's get specific and really break down what happens when corrosion gets out of control.
The fallout from corrosion is just massive. I mean, on a smaller scale, you've got things like machines not running as well as they should or products getting contaminated. But when you scale it up, you're talking about catastrophic failures. Think bridges, pipelines, the big stuff. And the cost to fix or replace it all? It's huge. The bottom line for you as an engineer is that fighting corrosion isn't just about saving money, it's about reliability and saving lives.
Pretty much all corrosion falls into one of these two buckets. Think of it like a fundamental fork in the road. Is the metal being attacked directly by gases in a dry environment? That's path one. Or is there a liquid involved, some kind of conductive fluid, that turns the whole thing into a tiny little battery? That's path two.
So let's take that first path and do a deep dive into dry corrosion. This is corrosion at its most basic level, right? It's a straight-up chemical reaction between a metal and the gases floating around it, like oxygen. The key thing to remember here is no liquid needed.
Now, under this dry corrosion umbrella, we're going to focus on these three main types. They're all important, but the one you are going to see everywhere, and I mean everywhere, is the first one: oxidation. That's your classic rust and tarnish story.
So how does this actually work? Well, you can think of it like a little three-step chemical dance. First, you've got a metal atom on the surface. We'll call it M, and it gives away 2 electrons. Now it's a positive ion. Then, step 2, an oxygen atom from the air comes along and snags those 2 electrons, making it a negative ion. And finally, opposites attract. The positive metal ion and the negative oxygen ion combine, and poof, you've got a thin film of metal oxide right there on the surface.
And this brings us to a super important concept for your exam, the Pilling-Bedworth rule. Now, here's the cool part. Not all of those oxide films are created equal. Some of them actually stop corrosion in its tracks. It all depends on the volume. If that oxide layer is bigger, bulkier than the metal it replaced, it forms this dense, non-porous shield that's protective. Think of aluminum. But if the oxide is smaller, the film ends up being all porous and cracked, which just lets the attack keep going.
Hydrogen can be a real troublemaker too. At room temperature, these tiny little hydrogen atoms can sneak into a metal, team up to form hydrogen gas, and build up this insane internal pressure that causes blisters and cracks. But crank up the heat, and it does something totally different. It actually starts pulling carbon out of steel, forming methane gas, and weakening the metal from the inside out. That process is called decarburization.
Okay, time to switch gears. Let's head down that second path we talked about: wet corrosion. The one thing you absolutely have to have for this to happen is an electrolyte. That's usually water, but it's any liquid that can conduct ions and, you guessed it, complete an electrical circuit.
This is where that whole mini battery idea really comes to life. See, when you have an electrolyte, different parts of the same piece of metal can start playing different roles. One area becomes the anode. That's the spot that corrodes and gives up electrons. Another spot becomes the cathode, which accepts those electrons. The electrolyte connects the two, the circuit is complete, and the corrosion party gets started.
Now, this right here is the classic recipe for rust, and you absolutely need to know this process. Let's walk through it. Step 1. At one spot, the anode, an iron atom gives up a couple of electrons and dissolves into the water. Step 2. Those electrons don't just stay there. They travel through the metal to a different spot, the cathode.
Step 3, over at the cathode, those electrons meet up with oxygen and water and form hydroxide ions. And step 4 is the grand finale. The iron ions from the anode and the hydroxide ions from the cathode meet up in the water and combine to eventually form that reddish-brown stuff we all know as rust. Okay, now that we've got the basics of wet corrosion, let's zoom in on two super common, incredibly important types. And listen up, because I can pretty much guarantee these are high-value topics for your exam.
Making this distinction is just so critical. Galvanic corrosion happens when you have two different metals touching each other. Think a steel bolt on a copper plate. Differential aeration corrosion, though, is a bit sneakier. It happens on a single piece of metal, but that metal is in an environment where one part has more oxygen than another.
This quote nails the principle of galvanic corrosion perfectly. It really all comes down to which metal is more chemically active. The rule is simple. The more active metal always becomes the anode. It sacrifices itself to protect the less active metal. So think about putting steel screws in a brass doorknob. The iron in the steel is more active than the copper in the brass. So guess what? The screw will rust away like crazy, acting as a sacrificial anode to protect that brass.
All right, let's solve a classic real-world puzzle. We've all seen this, right? A metal post sticking out of the water or the ground. Why does it always seem to rust the worst right at the waterline? Well, the answer is differential aeration.
It's the perfect setup for a corrosion cell. The part of the post that's deep underwater is starved for oxygen, but the part right at the surface is getting plenty. This difference in oxygen creates an anode and a cathode on the same piece of metal. The area with less oxygen, just below the water, becomes the anode, and it corrodes like crazy. Meanwhile, the area with more oxygen, right at the waterline, becomes the cathode and stays protected.
All right, we have covered a ton of ground here, from the big picture definition down to the nitty-gritty mechanisms. So let's boil all of this down into the most critical points you absolutely have to take with you.
Okay, this slide right here is your final checklist. It all starts with that big split. Is it dry corrosion from gases or wet corrosion that needs an electrolyte to make a little battery? For dry corrosion, you got to remember the Pilling-Bedworth rule. That tells you if the oxide layer will protect the metal. For wet corrosion, know the difference between the anode, which is where all the damage happens, and the cathode. And please, be ready to explain the difference between galvanic corrosion, that's two different metals, and differential aeration, which is all about different oxygen levels on the same metal. If you've got these concepts down, you are in fantastic shape for your exam.
And there you have it, our deep dive into how corrosion works. For an engineer, remember, understanding why something fails is always the most important first step toward designing something that won't. So now you know the enemy. The real question is, how do you fight it? What's your first move? Are you going to choose a different material, slap on a protective coating, or maybe even try to change the environment itself? Think about it.